The MML command, the language that keeps telecom networks alive introduction. Every time you make a phone call, send a text message, or browse the internet on your mobile device, there's a complex system of machines working silently in the background to make that happen. Towers transmit signals. Base stations process data. Core network elements route calls and sessions. And behind all of those machines, keeping them alive and running, are engineers who speak to those machines in a very special language called MML. MML stands for Man-Machine Language. It is a command line interface used to configure, monitor, troubleshoot, and manage telecom equipment. This includes base transceiver stations, BTS, base station controllers, BSC, mobile switching centers, master science, radio network controllers, RNC, and various core network elements. Engineers type commands into a terminal. The machine reads those commands and responds with data, alerts, or confirmation of changes made. It sounds simple, but in practice, MML is one of the most powerful tools in the telecom engineer's toolkit, and understanding it deeply makes a difference between a stable network and one that fails thousands of users at a time. This article explains what MML is, how it works, why it matters, and how engineers use it every single day. Whether you are new to telecom or simply want to understand what goes on behind the scenes of the networks we all depend on, this is your guide. A brief history, where MML came from. MML did not appear out of nowhere. It was developed as part of an international effort to standardize how human engineers communicate with telecom machines. The International Telecommunication Union, ITU, defined the MML standard under the Z.300 series of recommendations. This gave telecom equipment manufacturers a common framework so that an engineer trained on one vendor's equipment could recognize and adapt to another vendor's system with minimal difficulty. In the early days of telecom, every equipment manufacturer had its own proprietary interface. Ericsson had one way of doing things, Huawei had another, Nokia had yet another. This made training engineers expensive and created confusion whenever a network operator changed vendors or introduced mixed vendor infrastructure. The MML standard helped unify the approach, giving a consistent command structure across different platforms. Today, while vendors still have their own extensions and syntax variations, the underlying logic of MML, type commands that query or modify machine states, remains consistent across most telecom infrastructure worldwide. How MML works. The basics. At its core, MML is a text-based command interface. An engineer opens a terminal, connects to a network element, either directly or through a network management system, and types commands. The machine responds. MML commands typically follow a structured format. A command usually starts with a verb-like action word, followed by the object being acted upon, and then any parameters needed to complete the action. For example, a command might say display the status of a specific cell or add a new neighbor relationship between two cells. The syntax may look technical, but each command has a clear purpose. Commands generally fall into a few broad categories. There are commands to display information. These are read-only commands used for monitoring and diagnostics. There are commands to add, modify, or delete configuration. These change the way equipment operates. There are commands to activate or deactivate features or network elements. And there are commands to manage alarms and faults. Together, these categories cover almost everything an engineer would need to do during the day-to-day management of a telecom network. Use cases. Where and when engineers use MML1. Network configuration during commissioning. When a new BTS or cell site is being set up for the first time, engineers use MML commands to configure it from scratch. This includes defining the cell's identity, setting the frequency bands it will use, configuring transmission parameters, and establishing its relationship to the BSC or RNC that controls it. Without this initial configuration, the cell cannot go live. For example, an engineer might use a command to create a new cell object in the BSC, assigning it a cell global identity, CGI, setting the BCCH broadcast control channel frequency, and defining its maximum power output. Each of these steps is done through a specific MML command. The engineer types a command, checks the response, and moves on to the next step. It is methodical and precise. This commissioning process is critical. Any mistake in the configuration, a wrong frequency, an incorrect neighbor list, a misconfigured handover parameter, can result in poor coverage, dropped calls, or interference. MML gives the engineer precise control over every parameter, ensuring the cell is set up exactly as the network design requires. 2. Routine performance monitoring. Once a network is live, engineers use MML commands daily to check its performance. These are display commands. They do not change anything. They only read data. Engineers query cell traffic statistics, check handover success rates, monitor call drop rates, and review congestion levels. This kind of monitoring is proactive. Rather than waiting for users to complain that calls are dropping, engineers watch the data and catch problems early. If a particular cell shows a declining handover success rate, for example, the engineer might use MML to check the neighbor cell list and find that a neighbor has been removed or is blocked. They can then use another command to correct the configuration before the problem becomes widespread. Performance monitoring through MML is also used to feed into regular reports. Engineers run queries at the end of the day or week, extract data from specific cells or groups of cells, and use that data to assess network health. This supports capacity planning, quality of service reviews, and regulatory compliance reporting. 3. Fault management and alarm handling. Telecom equipment generates alarms when something goes wrong. These alarms appear in network management systems, but engineers often use MML to get deeper detail on what exactly the fault is and which component is affected. An MML command can display the current active alarms on a network element, providing the alarm code, severity, time of occurrence, and the specific hardware or software component that triggered it. The engineer can then use this information to diagnose and resolve the fault. For example, if a BTS raises an alarm indicating that a transceiver, TRX, has failed, the engineer might use MML to check the TRX status, confirm the failure, and then use another command to block the TRX so it does not interfere with traffic on the remaining healthy transceivers. Once the hardware is replaced or repaired, the engineer uses another command to unblock the TRX and bring it back into service. This workflow, display alarm, diagnose, block, repair, unblock, is a common pattern in telecom maintenance, and MML is a tool that makes each step possible. 4. Neighbor cell management. In a mobile network, when a phone moves from one cell's coverage area to another, the network needs to perform a handover. For this to happen smoothly, the source cell must know about the neighboring cells, their identities, frequencies, and characteristics. This neighbor list is stored in the BSC or RNC and must be configured correctly. Engineers use MML to add, remove, and display neighbor cell relationships. If a new cell site is added to the network, engineers must update the neighbor list of all surrounding cells so that phones can hand over to and from the new site. If two cells are generating interference with each other, engineers might remove them from each other's neighbor list to reduce the problem. Neighbor management sounds straightforward, but in a large network with hundreds or thousands of cells, it becomes a significant operational challenge. MML commands make it manageable by allowing engineers to view existing neighbor relationships, identify missing or incorrect neighbors, and make targeted changes without affecting the broader network. 5. Software and feature management. Telecom equipment receives software upgrades and feature updates regularly. Engineers use MML to manage these processes, activating new features, deactivating obsolete ones, loading new software packages, and checking the software version running on any given network element. Before a major software upgrade, engineers use MML to capture a snapshot of the current configuration, all the parameters, cell definitions, neighbor lists, and settings. This snapshot serves as a rollback point. If the upgrade causes problems, the engineer can use MML commands to restore the previous configuration. Feature activation is another important use case. Vendors regularly release new radio features, power control improvements, interference mitigation techniques, new scheduling algorithms. Engineers use MML to activate these features on specific cells or groups of cells, often as part of a controlled trial before rolling them out across the entire network. 6. Capacity management. As more users join a network and data consumption grows, engineers must manage capacity carefully. MML commands allow engineers to check how many traffic channels are configured and active on a cell, see how much of that capacity is being used, and add or remove channels based on demand. In GSM networks, for example, engineers can use MML to add additional TRXs to a cell that is consistently experiencing congestion. Each TRX provides additional traffic channels, allowing more simultaneous calls. Conversely, If a cell is underutilized, engineers might remove a TRX to free up hardware resources for use elsewhere. In 3G and 4G networks, capacitor management is more complex, but the principle is the same. MML commands allow engineers to see how the network is loaded and make targeted adjustments to improve efficiency and user experience. The significance of MML commands. It is easy to underestimate the importance of MML. On the surface, it looks like just a command line tool, something an engineer types into to get information or make changes. But its significance runs much deeper. Precision and control. Telecom networks carry critical communications, emergency calls, financial transactions, healthcare monitoring, and everyday personal communication. The parameters that govern how these networks behave must be precisely set. MML gives engineers the ability to set those parameters with exactness that graphical interfaces often cannot match. When an engineer types an MML command, they are specifying exactly what they want to happen, with no ambiguity. There is no clicking through menus where it is possible to accidentally change a setting without realizing it. Every command is deliberate, and every response confirms what was done. This precision reduces the risk of configuration errors that could affect service quality. Speed of deployment. When a telecom operator needs to deploy a new feature across hundreds of cell sites quickly, perhaps in response to a competitor or a sudden shift in traffic patterns, MML enables that speed. Engineers can write scripts that execute MML commands in sequence across multiple network elements, making large-scale changes in hours rather than days. This scripting capability is one of the most powerful aspects of MML. Rather than manually logging into each BSC and typing commands one by one, an experienced engineer can create a script that automates the process, checks for errors at each step, and reports on the outcome. This is how modern telecom operators manage the scale of their networks without needing an army of manual operators. Documentation and auditability. Every MML command that is executed leaves a log. This log shows who executed the command, when they executed it, what the command was, and what the system's response was. This audit trail is invaluable for troubleshooting, compliance, and change management. If a network problem occurs after a change is made, engineers can review the MML logs to see exactly what was changed and when. This helps isolate the cause quickly and either reverse the change or implement a correction. In regulated environments, this audit trail also supports compliance requirements that telecom operators must meet. Vendor independence of skill. While MML syntax varies between vendors, the underlying logic and structure is consistent. An engineer who has mastered MML on Ericsson equipment can learn Huawei or Nokia MML significantly faster than someone starting from zero. This transferability of skills is valuable in a global industry where engineers frequently move between operators and vendors. It also supports knowledge sharing within teams. Engineers document common MML procedures in runbooks and knowledge bases, creating a library of tested commands that can be used by others. This reduces the risk of errors and speeds up the resolution of common issues. Common MML command procedures, step by step. To make this concrete, here is a look at some common MML procedures and how they are typically carried out. Displaying cell status. An engineer wanting to check the operational status of a specific cell would typically start with a display command that queries the cell object. The system responds with a table showing the cell's administrative state, whether it is locked or unlocked, its operational state, whether it is functional, and any active alarms or faults. This gives the engineer a quick picture of the cell's health. If the cell shows as blocked or degraded, the engineer can then run further display commands to check the individual components, transceivers, antennas, transmission links, and identify where the problem lies. Adding a new cell. When commissioning a new cell, the engineer first adds the cell object to the BSC, providing its identifier and basic parameters. They then add the cell's radio channels, specifying frequency assignments and channel types. Next, they configure the cell's coverage and handover parameters, and finally they add neighbor cell relationships. Each step is a separate MML command, and the engineer typically works from a commissioning script or checklist to ensure nothing is missed. Once all the parameters are in place, the engineer uses a command to unlock the cell, bringing it into service. At this point, the cell begins transmitting and accepting traffic. Handling a hardware alarm. When a hardware alarm appears, the engineer uses a display command to query the active alarms on the affected network element. They identify the alarm code and look up its meaning in the vendor documentation. They then use a specific display command to check the status of the affected component. For example, a TRX that has lost its signal. If the component needs to be taken out of service for maintenance, the engineer uses a block command to remove it from active use while keeping the rest of the network element running. After the hardware is repaired or replaced, the engineer uses an unblock command to return it to service, and then confirm with a final display command that it is now operational and alarm-free. Software upgrade preparation. Before a software upgrade, the engineer runs a series of display commands to capture the current state of the network element, its software version, its active features, and key configuration parameters. This data is saved as a reference. If the upgrade causes issues, the engineer has a clear record of what the previous state looked like and can use MML commands to restore it. Best practices when working with MML. Experienced telecom engineers do not just know the commands, they know how to use them safely and effectively. Over years of working with live networks, a set of best practices has emerged that every engineer should follow. The first principle is always to display before you modify. Before making any change to a network element, run the appropriate display command to capture the current state. Know what exists before you change it. This serves as both a reference point and a safety net. If something goes wrong after your change, you have a clear record of what the configuration looked like before you touched it. The second principle is to test on one before touching many. When deploying a new configuration change or activating a new feature, do it on a single cell or network element first. Observe the results. Check the alarms. Review the statistics. Only if everything looks healthy should you proceed to roll it out across more sites. Scripts that automate changes across hundreds of sites are powerful, but they can cause widespread damage if the change is incorrect. Testing first limits the blast radius of any mistake. The third principle is to document every change. Even if the MML system logs commands automatically, engineers should keep their own records of what they changed, why they changed it, and what the outcome was. This documentation becomes invaluable during troubleshooting, during audits, and when new engineers need to understand the history of a network configuration. The fourth principle is to understand a command before executing it. MML commands on live networks have real consequences. A command that blocks a cell removes it from service, affecting all users in that coverage area. A command that changes a frequency assignment can cause interference. Engineers should always understand exactly what a command will do before they run it, and when in doubt, they should consult documentation or a more experienced colleague. Following these practices separates good engineers from great ones, and it is what keeps networks stable even as changes are made constantly behind the scenes. MML in modern and next-generation networks. With the rollout of 4G, LTE, and 5G networks, the tools engineers use have evolved. Network management has become increasingly automated, and many tasks that used to require manual MML commands are now handled by automated systems and self-organizing network SUN functions. However, MML has not become obsolete. It remains a go-to tool for hands-on troubleshooting, fine-grained configuration, and situations where automated systems fail or produce unexpected results. In 4G and 5G environments, MML commands are used to manage eNode Bs and gNode Bs, configure carrier aggregation parameters, manage radio resource management settings, and troubleshoot interface issues between the radio and core network. The syntax may look different from classic 2G and 3G MML, but the philosophy is the same: precise, deliberate, log commands that give engineers direct control over their equipment. As networks become more software-defined and virtualized, some elements of MML are being absorbed into API-based management frameworks. But for the foreseeable future, especially in the maintenance of legacy and mixed-generation networks, MML remains a core competency for telecom engineers worldwide. Conclusion: MML, man-machine language, is far more than a technical curiosity. It is a precise, powerful, and proven language through which engineers control the infrastructure that billions of people rely on every day. From the first configuration of a new cell site to the resolution of a live network fault, from routine performance monitoring to large-scale feature deployments, MML commands are the tools that make these actions possible. Its significance lies not just in what it does, but in how it does it, with precision, with speed, with a complete audit trail, and with a structure that engineers can learn, share, and build upon. In a world where connectivity is as essential as electricity or running water, the people who keep networks alive need tools that are equal to that responsibility. MML is one of those tools, and it has earned its place at the heart of telecom operations. For any engineer entering the telecom industry, learning MML is not just a professional asset, it is a fundamental skill. And for anyone curious about how the networks we depend on are built and maintained, understanding MML is a window into the invisible world of work that keeps the modern world connected. Thank you for watching.